Hello, are you ready? You have paper, pencil? Okay, let's start. So far we have learned how to solve quadratic equations using factorization. But what an equation is not factorable? Today we are going to learn another method which is called completing the square. The difficulty with solving quadratic equation is that unlike linear equation, we cannot isolate the variable. We have x squared, we have x, they're not like terms, we cannot combine them. Even if you move c to the right side, we still have x in two places here, which is not really helpful. So what we are going to do, we are going to learn how to magically transform this equation into a form which contains a perfect square. So our x will be localized. It will appear only once, and the perfect square will be equal to some number. So then by undoing operations, undoing squaring, we will be able to find x alone. But this is our goal. So let's look at the example how to do it. We'll start with an easy example with the leading coefficient a being 1. We will start with subtracting 5 from both sides. We are going to focus on this part of the equation, so we don't want this 5 to interfere. So we end up with x squared minus 6x equals negative 5. So now we want to transform this part of the equation into a perfect square trinomial. So we will have to add something to make it a perfect square trinomial. Of course, we will have to add the same something to the right side, so we keep our equation balanced. The question is, what is that number that we need to add to both sides? So again, we want perfect square trinomial here. So let's build it. The first term will be x, because x is what's being squared here. Now, we know that 6x is a double product. Double product of what? It must be a 3, actually negative 3, in order to create negative 6 as a double product. So then the square of the second term will be 9. So that's what we will need to add. Let's check that. X squared, square of the first, minus 3 squared, square of the second, with a plus, and the double product will be negative 3 times x, twice negative 6x plus 9. So this is actually the perfect square. Because we added 9 to the left side, we need to add 9 to the right side. So that becomes negative 5 plus 9, 4. Or we can go back here and say 4 on the right side. So this is our perfect square format that we wanted. From here, we are going to take a square root of each side. On the left side, we're just unsquaring. So before squaring, it was x minus 3. On the right side, it will be 2, you think? Maybe, but not necessarily. Because before squaring, it actually could be negative 2, because both 2 and negative 2 when squared gives us 4. We didn't know in advance what it was before we squared it. So we must write plus or minus 2 here. And that gives us two options. If it's a plus 2, then it's a little equation, x minus 3 equals 2, and then x equals 5. Or it could be x minus 3, which is negative 2, and then if you add 3 to both sides, it's x equals 1. So that gives us two solutions to our quadratic equation. You can say legitimately that this equation is much easier to solve by factoring, and it's true. Let's look back at it. So yeah, it's really easy to factor this one, x and x. 5 doesn't have a choice to be broken up as 5 and 1, and it should be minus minus to make a positive 5, and then middle term gives us minus 5x minus 6 minus x and the total is negative 6x. So the solutions are 5 and 1. True. So for this specific example, completing the square is not the best option, but I started with this because it's pretty simple. So let's see now when the quadratic equation is not factorable. The second equation is not factorable. It's kind of obvious. You may try if you want. So we are using exactly the same procedure. We want to get rid of everything except the x part. We want to focus on completing the square part, so we are going to add 3 to both sides. Whatever we do to left side, we must do to the right side, because we want to keep it balanced. It's an equation. We want to make sure that the left side and the right side are always equal. That gives us x squared minus 10x equals 3. Notice again, I left space here for that magic number that will complete the perfect square. So we want this to be a perfect square trinomial. So what it should be? The first term is x, because this is square of x. This is something else, but in the middle we have double product. Double product of what? If you take 10, actually negative 10, divide by 2, and it gives us 5. So 5 is that second term, again, negative 5 really, because it's a minus here. 5 is that number that will create double product. Minus x times 5 will give us negative 5x double negative 5x. So to complete the perfect square, we need to square the second term, so it will be plus 25. And of course, because we added 25 to the left side, we must add 25 to the right side to keep it balanced. So x minus 5 squared, it's a perfect square on the left, and 28, whatever happened on the right, 28. We are going to do the same thing now. We are going to unsquare both sides. On the left side, it's just x minus 5. On the right side, you think it's square root of 28. Sometimes, and sometimes it's negative square root of 28. Again, before we squared that number, it could be either positive or negative. So we have two options again. X minus 5 equals square root of 28, or x minus 5 equals negative square root of 28. And then we need to add 5 in both cases to get x equals 5 plus radical 28, or x equals 5 minus radical 28. We still need to simplify the square root of 28 because it's not as simple in simplest form. So to do this, let's recall, we need to find the perfect square that goes into 28. So it's a 4. 4 times 7 is 28. Then we break it into two square roots, square root of 4, square root of 7, and square root of 4 is actually 2. So this will be our final answer. We will work more later on reviewing square roots, how to simplify radicals. But for now, this is our final answer. We can actually combine them into a single expression, although these are two separate numbers. Okay, let's look at a harder example when the leading coefficient is not 1. The truth is, for equations like this method is not even preferable because it's really difficult. We still need to understand how to do it because this process, in fact, will allow us to derive the quadratic formula soon. So let's follow very closely what the steps are here. In fact, we are going to make it into a equals 1 by dividing all parts of the equation by 2. So we just get rid of this 2, and that will give us leading coefficient 1. But that will make our coefficients worse. This one is not too bad. But this one was an odd number, so we end up with 3/2. Not very pleasant. 0 over 2 doesn't care, it's still 0. We are still following the same exactly steps. We are subtracting that extra number, minus 3/2, from both sides. And we have x squared plus 4x plus something, I don't know yet what, equals minus 3/2 on the right side. We already much smarter than we were 10 minutes ago, so we know what should go here. It should be x plus what to create a perfect square? 4. We know that this x gives us x squared. Whatever goes here will give us that square. 4x is a double product, so this number must be 2. Then 2 squared is 4, and that is our perfect square expression. On the right side, we also need to add 4 to the right side to keep our equation balanced. That's not very pleasant, so we will need to subtract 4 minus 3/2. Let's keep it in the fraction form. So I need to rewrite 4 as 8/2 minus 3/2. That gives me 5/2. We could also use decimals. And then the next step is the same. We are taking square root of each side, x plus 2 equal. And again, it could be either positive or negative square root of 5/2. And to finish that, we need to subtract 2 from each side. So x equals minus 2, either plus or minus square root 5/2. This equation is not really in the simplified form, but we are not really worried about this right now. So once again, this method is not very nice for harder equations when the leading coefficient is not 1. As you see, the process is not very easy and the answer doesn't look pretty. But we actually do need to understand this process in order to derive the quadratic formula. And for simple equations, it's actually a nice method. Good luck.